Madam Mansa, madam, good morning, madam. Hello.
Sir, good morning, sir.
Just will check voice check. Voice man వినిపిస్తుందా?
Yes, sir. Yes, sir. Pani వినిపిస్తుంది, sir.
Okay, thank you.
Okay, sir. Good morning, everyone. We'll start the session in few minutes. I request all the participants just hold on for few minutes. Good morning, participants. Am I audible? Just somebody please confirm me. Dear participants, am I audible? Thank you. Thank you. Good morning, everyone. I'm Manasa, professor in the Department of Civil Engineering, SVCW. Just we had a small announcement for you. That is, today's morning and evening sessions are interchanged. At this morning session, Mari Saminathan, as having committed to some other work, has requested us as to that he will take the afternoon session, so that this session would be addressed by Dr. Pala Girish Kumar. Just we are extremely sorry for the inconvenience. This session is going to be addressed by Dr. Pala Girish Kumar, and the afternoon session will be addressed by Dr. Saminathan. Okay. As you all well know that on behalf of our Civil Engineering Department, SVCW, we're organizing we are organizing a short-term training program on soft computing techniques in civil engineering. This is phase 3 training program. And also, as you all well aware of that sessions ahead, today's session is going to be headed by Dr. Pala Girish Kumar, who is head of the Civil Engineering Department at SVCW. Now, let me take the privilege of introducing him. Dr. Pala Girish Kumar was graduated in civil engineering from Sri Venkateshwara University College of Engineering, Tirupati in 2012. He has done his master's in transportation engineering and management from National Institute of Technology, Tiruchirappalli, 2014. And he also done his PhD in civil engineering from National Institute of Technology, Tiruchirappalli, in 2018. Forward to SVCW, he worked as an assistant professor from 2018 to 19 at Godlavalaru Engineering College. And also in 2019, he joined as an associate professor at Sri Vishnu Engineering College for Women, which is autonomous Bhimvaram. And at a very adolescent age, he has been delegated as the head of the Civil Engineering Department at SVCW. Coming to his work areas and his achievements, he has guided one MTech dissertation and 15 UG projects in the areas of pedestrian traffic, self-healing pavements, simulation, route optimization, RAP, and also many more. Apart from that, he has been invited as a speaker by multifarious institutions and organizations. Besides all these technical aspects, Dr. Pala has been a rock solid performer in the area of administration and external affairs too. He is the prime mover and instigator of Royal Civil Colloquium, that is RCC, which is established in the year 2019, whose cardinal motto is to expose women students to the technical and industrial aspects of working areas. Dr. Pala Girish Kumar has also been the founder of the Career Development Program, which is called CDP in short in SVCW, that functions in indulging technical and non-technical skills. He also reinstated the ISTE student chapter in SVCW, and he also holds a lifetime membership in professional bodies like Indian Geotechnical Society, which is IGS, and Institute of Engineers, India. In addition to all this institutional flourishments, he had also organized several workshops for the faculty and the students as well. And also, he has been consistently working on various virtual programs like String Web Series, Digital Wiring 2K20, that is an online event platform, short term training programs, AICTE sponsored programs, and also been the edge of organizing SCTAC 2020. Besides all this, he has been honored with National Award from the Government of Tamil Nadu for the best project during the year 2014, Best Paper Award for the paper presented in international conference, which is Peace 2018 at NIT Tiruchi, and also won the International Best Researcher Award of the year 2020 in the area of terra mechanics and nanomaterials in pavements from IDBAS Learning Center, Malaysia, and World Research Council. Dr. Pala was induced as the reviewer of Transportation Research Board, International Journal of Engineering Sciences Advancements, Advanced Computing and Biotechnology, and Global Journal of Research in Engineering, USA. He has also blazoned 12 publications at international conferences, 3 at national conferences, 14 plus publications in the international and national journals, and also he had a book in his account. Dr. Pala's areas of interest relates to terra mechanisms and nanomaterials in pavements, traffic safety, pedestrian and driver behavior analysis, self-healing pavement evaluation and management, and traffic simulation. These are his areas of interest. With this brief introduction, I'd like to hand over the entire session to Dr. Pala Girish Kumar. Dr. Girish, sir, please take over the stage.
Thank you, madam. Thank you so much.
Sir, you're
Thank
not
you. My
audible.
voice is audible to all.
Sir,
I'm not audible.
it's a bit disturbances there, sir. Just
Okay. Hello.
sir. A small
Hello. My voice is
disruption.
audible now, madam.
Yes, sir. Yes, sir. Now it is audible.
Yes. Now it is audible. Okay. I thank you very much for the introduction, madam. I request the participants to mute. My voice is clear now.
Yes, sir. Yes, sir. Your
Thank you.
voice is clear.
Yes, thank you, ma'am. At any point of time, if there is any breakage, please interrupt me, madam, so that
Okay,
I
sir.
will be aware of that. Okay.
Okay, sir.
So
Sure,
I'll
sir.
quickly share my screen and I'll start the session. Are you able to see my screen, ma'am? Hello?
Yes, sir. You can continue. Your audible, sir.
Okay. Thank you. Thank you. Good morning to all the participants. Yeah. Thank you for the nice introduction, Ms. Manasa, madam. Yes, today my presentation topic for this AICTE program on this session is mobility performance of planetary rovers. Since in the phase 1, phase 2, I gave a quick introduction about the terra mechanics area, and phase 2, I talked about FEM applications in terra mechanics. Maybe I can see few people who are newly added to this phase 3. So for that, I would like to quickly give some basic introduction about the terra mechanics, and after that, I would like to talk about the mobility performance of the planetary rovers. So with this, I will straight away go to the outline of my presentation. Here is my outline of presentation. I'll start with giving a definition of terra mechanics, and I'll talk about what is this terra mechanics and what are the things that we can do in terra mechanics, and little basic brief introduction about terra mechanics, and then I will try to show the types of rovers and landing sites that are available. And then in particularly in this session, I'll more importantly concentrate on delivering the session and discuss with you about this mobility performance, which is coming under the trafficability studies. And then later I will try to summarize the entire presentation, and then I'll show what are the research contributions that we made through this research work. and then I will try to show the publication which you can take as a reference for this entire research work that was carried out. And then I will also try to give you some research scope of this area. With this, I will try to define you what is terra mechanics. Yes, this terra mechanics is something which deals with the study of soil properties and exclusively the interaction of wheeled or tracked vehicles on various surfaces. When I say various surfaces, here we have two types of surfaces. One is the terrestrial surface, one is the extraterrestrial surface. Here, when I talk the terrestrial surface, it is nothing but the Earth surface. When I say extraterrestrial surface, it is the planetary surface. Okay, I'll talk in deep about the extraterrestrial surface in subsequent slides. So here I have mentioned wheeled vehicle, tracked vehicle. So here I am talking about the terra mechanics. Here one thing you should understand, we are talking about the robots, mobile robots or autonomous vehicles, which is nothing but unnamed vehicle, unmanned vehicle. Okay, so it is we are having two mechanisms. One is the wheeled mechanism, so we call it as a wheeled vehicle. We have a tracked mechanism, we are calling it as tracked vehicles. Okay, so we will also see what is the basic changes of these two things and the various things that comes under this terra mechanics. So basically, this terra mechanics is nothing but the study of soil properties, exclusively the interaction between the wheeled vehicle or a tracked vehicles on various surfaces. You can see the picture that represents, the wheeled type of mechanism, the mobile robot, and you can see the another picture which represents the tracked type, which is tracked vehicle, which is used to explore the space or which is used to explore different things. Yes. So finally, we understand the definition of terra mechanics, which is the study of soil properties, exclusively the interaction of wheel or a tracked vehicle on various surfaces. When I say various surfaces, it is terrestrial and extraterrestrial. Yes. So coming to the brief introduction of this terra mechanics, yeah, we are talking in particular about mobile robots, unmanned vehicles, or autonomous vehicles. Okay, so these mobile robots are very important in the exploration of space and it plays a vital role on planetary surfaces. When I say planetary surfaces, I mean to say the Martian surface, which is a Mars, or even you can call it as a red planet, and also moon surface, which is also called as lunar surface. And these planetary surfaces are mostly covered with lot of dust, loose soil, deformable soil, different types of rocks, stones, ditches, obstacles, and steeper slopes, and many more. Because of this, when the mobile robots are moving on such a challenging terrain, it will have a huge and higher risk, which can cause a severe slip and sinkage on that particular loose soil or deformable soil. Maybe sometimes there is a possibility, to get the wheel stuck in the loose soil or a deformable soil. Because of this reason, the rover mission may get failed, or maybe some other reason, like when it is traveling, the parts get diverted because of the presence of obstacles. So diverting its path from its original path is also becoming one of the major problem for us. Okay, so these are few things, few challenges that exist on the planetary terrain which we have to address. Okay, for example, if you see here, so many pictures I have represented, I have given in the bottom of the slide. Lunocode 1 MER, which is a Mars exploration rover, and Sojourner, and this in brackets I have mentioned some distance in kilometers: 10.5 kilometers, 7.73 kilometers, 100 meters, and these are the distances which is traveled by these particular rovers. Okay, but actually this rover is designed for a target distance to be traveled, but instead of fulfilling the desired distance, it is traveled only this certain distance and it got stopped and it got failed. For example, I talked here something regarding Luna 21, which is landed on the lunar surface in the year 1973, and it has traveled 37 kilometers, but the estimated target distance was 42 kilometers. So it was able to fail to travel further 5 more kilometers, and the mission got failed due to the reason the wheel got stuck in the loose soil during its traverse. So there are particular problems where we need to avoid such problems. It is necessary to study the mobility performance of the wheeled rover or a tracked rover, which is completely based on this terra mechanics area. When I say this mobility performance will be studied in terms of three performance indices, and I have namely given mention. I mean, the names of these three performance indices are mentioned in the slide. You can see the trafficability is one performance indices, and maneuverability is another performance indices. Terrainability is another performance indices. Here, terrainability is nothing but which is the rover or a rover's wheel ability which travels on soft soil or hard ground without any traction loss. And when you talk about maneuverability, it all deals with the environment, existing environment, the ability to navigate, the ability of the rover to navigate through different environmental conditions. Maybe it is a moist type or heavy wind type or a existing dust and so many other environmental problems. So okay, and another important performance indices is terrainability. So this is nothing but the rover ability to negotiate different terrain irregularities, the slopes, maybe adverse, mild, narrow, and so on, and different obstacles. So these are the various types of performance indices in which we were able to define the mobility performance of a planetary rover. When you talk about these three, the maneuverability and terrainability are related to the environment and the existing terrain conditions. So here we cannot change the natural existing condition. So therefore, we have a huge possibility of concentrating and do investigation on this trafficability parameter. So this is where we can really concentrate and do particular investigation, the experimental analysis, numerical simulation, and we were able to give a best optimal solution for the existing problems. Yes. So therefore, we found that we can conduct research on wheel soil interaction, which is based on completely this terra mechanics, in order to investigate the mobility performance of wheel on soil and also try to study various parameters that influences this traveling performance or mobility performance of a planetary rover. So when you do particular investigation, we'll hope the mobility performance of unstructured terrain of a plant rover can guarantee the mission get success. So here in this particular session, I will talk about the trafficability parameter in which I will try to give you the mobility performance of a planetary rover wheel. So here this trafficability gives us the mobility performance, and this mobility performance depends on various parameters. Okay, those parameters are given in this. Sinkage is one of the parameters that affects the mobility performance. We will try to see how the sinkage is affecting and impacting the mobility performance of a particular rover or a rover wheel. And also there is another important parameter which comes under this mobility performance, which is slip ratio. And another important parameter is drawbar pull. And another important parameter is resistance. Here this resistance is a combination of couple of resistance. The resistance is a combination of compaction resistance, bulldozing resistance, and gravitational resistance and rolling resistance. All these two together we call it as a motion resistance. So this motion resistance is one of the important parameter that plays vital role in in this mobility performance of particular rover or a rover wheel. And then we'll see about the torque and we'll see about the coefficients, different coefficients, and so on. So these are the certain parameters that are really affecting the mobility performance of a planetary rover or a rover wheel. So in this particularly, I considered this trafficability area, and I was able to conduct some kind of research on these parameters, and I try to evaluate the effect of each and every parameter on the mobility performance of a rover in this trafficability studies. These parameters are normally which is depends on the geometrical parameters. That is what I told, the influence of various parameters. Yes. So when I talk geometrical parameters, I talk about wheel weight, I talk about wheel diameter and wheel width. I'll talk about the closure of or lugs which can be introduced to the plane wheels, and this also can play an important role in improving the mobility performance of a particular rover. Yes, I'll try to show this slide about the different types of rovers that are available and different landing sites. In particular, I am talking about two planetary surfaces. One is the Martian surface, one is the lunar surface. In the Martian surface, we have a lot of rovers that are sent already to the planetary surface. I have mentioned here few important space rovers. That is, one of the rover is Spirit rover, another one is Opportunity rover, another one is Curiosity rover, and another one is Sojourner rover. So these are the few important rovers that are comes under this Mars exploration rovers. And when you talk about lunar exploration rovers, we have a lot of rovers that are available. But in particular, I will mention only few rovers. And you can see here Lunar Code 0 and Lunar Code 1, Apollo lunar roving vehicle missions. So in this Apollo category itself, so many Apollo missions are there, like Apollo 14, Apollo 16, Apollo 17, and so on. Many more are there in this particular Apollo lunar roving vehicle category. Okay. And there is one more thing, Lunar Code 2. So this is a figure that represents various landing sites on the planetary surface. As you know, this yellow indicates one kind of landing site, this green indicates another type of landing site, and this red indicates another type of landing site. You see this picture that gives you more clarity on this landing sites. This is the entire planetary surfaces, and you see Apollo 17, which is landed on the moon in the year 1972 on December 11th. So that is the place where this mission has landed. So it is called as Apollo 17 landing site. Okay. Likewise, you have seen so many points here. Okay. So suppose you say Apollo 11, which is landed on the moon, which is on 1969 on July 24th. So this particular, where is this particular place is Apollo 11 landing site. Like this, so many landing sites are there. Yes. No, this is set of crew. They are used to go there for the space exploration. Now we need to understand what is the necessity of doing this study. This Yeah, what is the necessity of doing this study? Yes, one should understand when a rover or a mobile robot is traveling on such a challenging terrain, there is a huge possibility to happen lot of problems. Maybe because of the terrain conditions, maybe because of the environmental conditions, maybe because of the the rover design of a rover. So in particular, we will concentrate more on the trafficability, where this trafficability involves more in the various model size parameters. So in designing a planetary rover, we need to evaluate the effect of model size parameters such as the wheel weight, wheel diameter, wheel width, and closures of wheel on its mobility performance. And this traveling performance more depends on the type of mechanism that you are introducing. That I already mentioned in the earlier slide, that as we have two types of mechanism. One is the wheeled mechanism, one is the tracked mechanism. The wheeled mechanism and tracked mechanism have two different type of results. For example, you take the entire rover weight. Okay, so if you are increasing the rover weight of a wheeled mechanism type, that is having an amount of significant amount of effect on the traveling performance. Where you talk about the tracked mechanism type of a rover, even you increase the rover weight, there will be very negligible effect on its traveling performance. Okay, so there are two types of mechanisms where your wheel weight is also playing an important role in giving its traveling performance. Okay, so here from the studies we were able to understand the wheel diameter rather than wheel width. Maybe there is a possibility to improve its traveling performance, and also the provision of lugs or introducing the grousers can also improve the traveling performance. Yeah. So we thought we need to pay some attention towards the dynamic effects of planted rover when it is interacting on the terrain interface. Most importantly, the slip and sinkage are the two main major parameters that affects the mobility performance of a rover or a roadway. So before going to design a rover, one needs to know its mobility, because if you are able to give a better distance, that is the main motto of this research study. So here, sinkage and rubber pull are the common measures of mobility. So with this, I will try to show what are the research objectives of the current study. So these are certain parametric study, or developing an improved model for a shear stress distribution, dynamic analysis of plane wheels. All these things are few research objectives. In this particular session, I will try to concentrate on this red color indicated red color objective, that is the trafficability studies of rigid plane and lugged wheels on TRI-1 lunar soil simulant. You see here TRI-1 lunar soil simulant is nothing but Tiruchirappalli-1 lunar soil simulant, which is India's first soil simulant, which is India's first simulant, which was characterized with the help of ISRO Bangalore. So on this particular simulant, we were able to conduct the experimental study, and we were able to draw some conclusions, and we were able to optimize the wheel dimensions with respect to the experimental and numerical simulation analysis. So with this, I will try to define and introduce the trafficability studies. What is this trafficability studies? What are the parameters? How it is influencing? How this can be find out? All these things we will see in the subsequent slides. Yes, when I say this is a picture that represents wheels on interaction mechanism. So this is the first one is the plane wheel. If you see here, this is a plane wheel, and this is a lugged wheel. Okay, the second line circle indicates the lugged one. So this is a lugged one, or the wheel with the grousers. So you can see different parameters, like different variables, the drawbar fx, fz, and tau of theta and sigma of theta and theta or theta f, and so on. Okay, in this particular study we will read everything. See, when this wheel starts contacting or starts contacting the surface when it's traveling, I mean when it starts traveling the deformable soil, always a complex interaction takes place at the wheel soil contact and in the adjacent soil. And when during its travel there is a possibility to cause two types of slips. Okay, one which is on a flat terrain, one which is on a slopy terrain. Okay, the slip which is causing on the flat terrain will be on the longitudinal direction. The one which is causing on the slope terrain will be in the lateral direction, and the one which is causing on the flat terrain, we call it as a slip ratio, and the one which is causing on the slopy terrain, we call it as a slip angle. So there are possibility of causing two types of flips during its motion on a planetary surface. It is given on flat terrain as well as sloping terrain. So to achieve a rover traveling much longer distance over challenging terrains, we need to perform, I mean, it has to perform more complex tasks, and it is needed to carry out research on improving the mobility performance of a rover or a rover wheel. And this performance of a rover or a rover wheel depends completely on the traffic wheel. Now let us see one by one the different parameters which gives us the mobility performance of a rover or a rover wheel. The first important parameter that gives or affects the mobility performance is the sinkage. Yeah, this sinkage is classified into two types. One is the static sinkage, another one is the dynamic sinkage. So the amount of sinkage that depends completely on the properties of soil, wheel dimensions, wheel shape, stiffness, and wheel load. Here it is classified into static and dynamic as I mentioned. The static is completely dependent on the wheel load, and it is defined as the amount of sinkage which is caused by the wheel before its travel. And this can be calculated using this empirical relation with the experimental results. And another classification is dynamic sinkage. This is completely depends on the wheel rotation, and it is defined as the amount of sinkage which is caused by the wheel after its travel for a particular distance. So this is defined as a dynamic sinkage. You see the two pictures which is represented in the bottom of the slide. One is indicating the static sinkage, another one is indicating the dynamic sinkage. Here you can see the sinkage which is caused due to the wheel weight, wheel load before its movement, and here you see the sinkage. You can see the wheel that is causing dynamic sinkage. It is because of the wheel rotation to a particular distance, the amount of sinkage that is taking place after the movement of this wheel to a particular distance. So this is defined as a dynamic sinkage, and this is defined as a static sinkage. So these two together we call it as a sinkage. So this is how we found out this particular parameter, and obviously we need to get a minimum sinkage. Okay, so in order to give a better mobility performance, and that sinkage can be obtained by using some empirical relations with the help of the experimental results. Yes, here you see Becker pressure sinkage model. He has given the empirical relations, which is a function of different quotient of quotient modulus and that sinkage exponent and wheel weight and diameter of wheel and width of the wheel. And also he has incorporated the Rees pressure sinkage relationship, and he has obtained two different empirical relations for the terrestrial surface as well as extraterrestrial surface, and the expressions are given in this table, you can see. And the bottom table represents different class that is defined based on the duct depth, which is nothing but a sinkage. Okay, so if you are able to get a less than 0.10 meters, it is acceptable, and which is getting more than 1.1 meters, it is avoidable. So the best possible mobility performance is this category, and this is the worst mobility performance of a particular rover. So like this, the acceptable rut depth class is given classified as acceptable and avoidable. So now this is another important parameter that defines and affects the mobility performance, which is slip ratio. And this is nothing but the difference between the translation and rotational velocity. And this normally ranges between 0 to 1. And this slip ratio 0 indicates, yes, this slip ratio 0 indicates the wheel moving forward without having any problem. Means which is without having any slip and without having any slippage. Okay, and unity, this one indicates the wheel experiencing higher risk, and it is having a huge slippage, and it is facing a difficulty while traversing on a particular terrain. So always we must get on a lower side. So the lower slip ratio you get, the better mobility that you are experiencing. So it is defined here, the minimum slip ratio always gives a better mobility of a particular rover or a rover wheel. So this is another important parameter that we are coming under the trafficability study. And another important study parameter is motion resistance, which I have mentioned, which is a combination of different resistance like compaction resistance, bulldozing resistance, gravitational resistance, and rolling resistance. Each resistance takes part according to certain conditions. Suppose you take a gravitational resistance, this comes into picture when your rover or a rover wheel subjected to travel on a sloped terrain. So like that, these resistances comes into picture according to the certain conditions. You know. So likewise, we were able to give a certain relationships for different resistance. Like you see the compaction resistance, which is a function of quotient modulus and friction modulus, and also the wheel parameters like B and D and sinkage exponent N. All these things were able to find out with the help of a geotechnical investigation, laboratory investigation, like conducting a shear test, conducting a compaction test, conducting a plate load test. You are able to define all the parameters, and you are going to input these things, and you are going to get the compaction resistance, bulldozing resistance, and gravitation resistance. As I mentioned, this gravitation resistance comes into picture when your rover is subjected to move on a sloping terrain. Okay, and also there is a reference for this. The maximum slope that are existing on a Mars is 30 to 40 degree. But so far, the wheeled rovers are designed only to the limited slope, that is 25 degrees. So this is where the area is existing to in order to do some more investigation, in order to accommodate such kind of a slopy areas, slopy terrains. Yes. So this is another rolling resistance, which is a function of quotient of rolling resistance, which is in turn function of Z. Z indicates the wheel sinkage here. D indicates the wheel diameter. So based on this, the quotient of friction changes. Based on the quotient of friction, the rolling resistance also matters. And always remember, the lower the resistance that you have, you are going to get the better mobility. So higher rolling resistance indicates poorer mobility. Lower rolling resistance gives you the better mobility. And also I have mentioned here references. Based on these references, we were able to get all this information. And then another important parameter, which is a drawbar pull. And this drawbar pull is nothing but the pulling force or pulling ability of a vehicle till it reaches maximum traction. And always remember, this drawbar pull must have a comes in a higher side. Okay, because we need to have a more pulling ability, then only your mobility performance will be in a better way. So the more the better drawbar pull indicates a better mobility, the poorer drawbar pull always indicates poorer mobility. Okay, so with this is what I was able to mention. There are different parameters that we studied in trafficability studies. One, we have seen sinkage. That sinkage is defined as static sinkage and dynamic sinkage. And also we have seen slip ratio, which is given in the range 0 to 1. 0 indicates better. 0 indicates wheel moving forward without any slippage. The unity indicates the wheel having a lot of difficulties during its travel because of higher slippage or sinkage. And also another parameter, motion resistance, we have seen, which is a combination of different resistance. And we have seen now drawbar pull. These are the four different parameters that we are going to see with a case study. Okay, so with the case study, we were able to see. Just give me a minute. Okay, thank you. So now we will try to see what are the wheel parameters that we were considered. So these are the various wheel parameters that we considered for the particular study. We categorize the wheel type of wheel as a small wheel and a large wheel. And the small wheel parameters are like, you see the wheel diameter, you see the wheel width, you see wheel weight, and also through the experiment we were able to see the wheel sinkage for that particular plane wheel, and also the traveling distance and traveling time. Finally, we were able to find out the velocity, speed. And also similarly, the large wheel parameters are also given like this. The small wheel, it is 160 by 32 and 210 by 50. And now this is the experimental setup that you can see, that which we are able to fabricate in our laboratory, and we were able to conduct the experiments on the TRM lunar soil simulant. Okay, and now these are the two pictures that represents the plane wheel and large wheel. This is how it looks like, and this is how it looks like. And this classification, like small wheel or large wheel, we have done based on a source called this Baladi and Rohani in 1984 given slip. This BBR ratio is nothing but wheel slip. So this wheel slip is defined as the wheel width to wheel radius, wheel diameter, and this must be ranging between zero point 0.2 to 0.5. So based on this source, we were able to fabricate these models, and we categorized these wheels into small and large, which is having a wheel slip of zero point 0.4. That is a wheel with wheel with width 160. Wheel with 160 mm diameter with a width of 32 mm, and large wheel with wheel slip as 0.47, and with its dimensions as 210 mm diameter and 50 mm wheel width. So that is the wheel configuration of for conducting experimental work, and this is the various combinations of small wheel as well as, sorry, this is a mistake. This is a large wheel. Okay, the down one is, the second table is large wheel. So in the first one is union. Earlier slide I have shown the plain wheel type, and in addition to that we took that Grouser's part. We have introduced the lugs. Okay, here you can see in the picture the different lugs are introduced. Okay, on a plane wheel. So in order to investigate the mobility performance with respect to the provision of number of lugs, and also these lugs are introduced as 8 number of lugs, 12 number of lugs, 16 number of lugs, and for each lug also we took certain height. So with the various combination of heights also we were able to investigate something in order to find out the most feasible optimal dimension of a wheel which gets the maximum mobility performance of that particular on particular TRM lunar soil simulant. Yes, you see here h equal to 5 mm, h equal to 10 mm, h equal to 15 mm. So here this grouser is provided in L shape, and this grouser height is given as 5 mm and 10 mm and 15 mm. So with different combinations, we were able to conduct lot of experiments, and from the experiments we were able to draw particular conclusions, and we were able to come up with an optimal solution for that particular problem. Yes. So you see here n equal to 18 and h equal to 5, 10, 15. We were able to have combinations for n equal to 12. We did experiment for when with h equal to 5 mm, with h equal to 10 mm, with h equal to 15 mm. Similarly, we used 16 number of lugs with 5 mm height, with 10 mm height, with 15 mm height. Likewise, we have done for large wheel also. Okay, so these are the different combinations that we consider for the experimental study, and you can see in this table the different weights of wheel. Okay, the different weights of wheel with respect to wheel slip. So the wheel slip always, you can change with respect to the diameter, or with respect to the diameter as well as with respect to the wheel width. So you can see the first table indicate the small wheel at constant width. When you use at constant width with the different diameters, when you use 5 mm height, you will get certain diameter. When you use h equal to 10 mm, you will get different diameter. So you are changing the diameter here. So with respect to different diameter, with respect to the constant width, what are the different weights and what are the wheel slip, that you can see in the table. And similarly for the large wheel, you can able to see here. And now I'll try to show, this is the picture that represents the experimental work, and this is the top view of the experimental work. We were able to conduct experiments. It is able to move for a particular distance, and we were able to measure this particular vector depth or a sinkage, and based on which we were able to conclude so many things, so many results. This is, we call it as a wheel sinkage studies, which is conducted in the laboratory on the TR1 lunar soil simulant. Yes. So now this is the table. Now we will see what is this wheel sinkage studies tells about. What are the particular results that it is giving us, and what we have to understand based on the results, that we will talk about this couple of slides. So you see the table here which I mentioned here, wheel parameters and TRI1 soil simulant properties, and these properties we were able to arrive and attain based on the geotechnical engineering laboratory tests such as shear test, compaction, as well as plate load test. And here this table represents the comparison of experimental results with the theoretical results. Yeah. Earlier we have seen when we are talking about sinkage parameter, we were able to see the Becker pressure sinkage relationship, which is given for the terrestrial and extraterrestrial surface. So taking that into account, we were able to predict the sinkage on moon as well as the sinkage on the terrestrial surface. So this is the extraterrestrial surface sinkage, and this is the terrestrial surface sinkage prediction. And this the last column indicates the experimental results that were obtained in the laboratory. So these are the right side you see, left side you see n equal to this is the number of lux combination, as well as this is the height. So for different combinations, we were able to get the experimental results. We were able to get the predicted values on the terrestrial as well as extraterrestrial surfaces. And now we need to understand something from this. You see the minimum sinkage obtained for this, when you use n equal to 16 and h equal to 5, you are able to get the experimental results, the minimum experimental results at this condition. Whereas if you see another other combinations, you are able to get certain the maximum things. Okay, the maximum arrived for when n equal to 12 and h equal to 15, you are able to get the experimental value. But another important most conclusion you can draw and infer from this table is, the predicted, if you compare the predicted values and the experimental values, the comparison holds good for particularly two cases. One is for the plane wheel, and another one is for a particular condition when n equal to h16 and h equal to 5, the experimental values falls under, falls less than the predicted values. See, when you go back into your structure or something, when you are do cross checking, verification check, when you are designing a beam or a column, definitely you are going to give some cross check. You will have that particular permissible limits. Okay, so you must have that, your result must come under below certain permissible limit. Similarly, the same thing you can apply here. Okay, so only these two conditions we are able to get under the permissible limit, but there are other cases we are exceeding the predicted values are, less compared to the experimental values. So here we understood something. There is a need to redefine the empirical relation in order to predict on the higher side, so that when you design a rover or a rover wheel, your experimental value will falls under the permissible limit, so that you can avoid such unnecessary unwanted problems. Okay, so similarly, this is for large wheel 216. This is 210 mm. This is another mistake. You have to excuse me. This is a 210 mm by 50 mm, and for this also we were able to tabulate the experimental results, and also we were able to find the predicted values for the terrestrial surface as well as extraterrestrial surface, and the similar trend we were able to notice, except two cases. All other cases, the predicted values are less compared to the predicted values are less compared to the experimental values. So these are the pictures that represents, you can see, this is this slide completely talks about the small wheel comparison, and the next slide I will show you that talks about the completely on the large wheel conditions. So when you see the first picture, this is the picture drawn, this is the plot, this is the graph plotted between the sinkage and wheel slip. The wheel slip, that is the ratio of the wheel width to wheel radius. I mentioned here R1 is nothing but R1 is the plane wheel diameter plus whatever h you are going to add. Like when you take grouser height as 5 mm, so that 5 mm will be added. When you take h equal to 10 mm, when you take h equal to 10, 20 or 15 mm, this respectively this R1 will change, but this B remains constant. So B as 32 mm. So with constant width, with different wheel diameters, what is its sinkage? How this various wheel diameters giving that sinkage? That is what we were able to plot here. The Z experimental as well as Z theoretical unknown for this particular number of flux n equal to 8, and similarly n equal to 12, n equal to 16. From this all graphs, you are able to understand the increase in the increase in wheel slip. Okay, so you are able to reduce the sinkage. So you are able to reduce the sinkage. You are getting the minimum sinkage for h equal to 5 mm. Okay, in this particular n equal to 8. Similarly, the same trends are happening like this with this two other cases when you use n equal to 12, n equal to 16. And similarly, when you use large wheel, the similar trend is happening here. The increase in wheel slip always shows you the reduction in sinkage, and you are able to get the minimum sinkage for this particular condition h equal to 5 mm at n equal to you know uh, 16. So when you compare when n equal to 8 to n equal to 12, n equal to 12 to n equal to 16, you are able to get the minimum sinkage at h equal to 5 mm when n equal to 16. And when you compare only within the number of flux, with constant number of flux, with increase in length height, with increase in wheel slip, okay, so you are able to get h equal to 5 mm, the minimum sinkage at h equal to 5 mm in that particular constant number of flux. So that is how the comparison is made. So finally, the conclusions are made like this. Experimental results holds good for particularly two cases. One is for the plane wheel diameter plus the luxury conditions when you use n equal to 16 and h equal to 5 mm, you are able to the experimental results on the lower side as compared to the predicted values, whereas all other combinations, your predicted values are false. Coming in under less category compared to the experimental values. So we were able to predict the rover actually moving on a moon can have a severe higher sinkage compared to the predicted sinkage on the extraterrestrial surface. So we need to, or we therefore we are able to understand there must be an attempt to be made to derive a new theoretical sinkage model that can predict a sinkage of a rover wheel or moon on a conservatively on a higher side with the maximum sinkage. So that is how we were able to introduce or develop a model by introducing two different parameters. So this table indicates the new empirical relationships given individually for small wheel and large wheel with respect to different number of lugs. But later we worked on these particular different empirical relationships, and we were able to develop a single unique model which is given in the below. Just excuse me. Just hold on for a second. Hello. Just hold on for a second. Hello. Please excuse me. Yeah, we will resume now. Thank you. So these are the individual empirical relationships are defined, but these are obtained based on the experimental results that that we arrive in the laboratory. So based on the experimental results, we were able to develop these individual relationships, and later by doing an extensive work, we were able to develop a unique model with the interaction of two different constants. So here the equations, the relationships for this sync case prediction on moon are given in terms of gravity effect and also wheel slip for both wheels. You can see here, you can even predict this, sinkage on lunar surface by using this empirical relation. The exp represents the experimental value, and A and B are the two sinkage constants which are introduced. And I will try to show this what is A and what is B in the subsequent slide. And effect of gravity on the terrestrial surface on the extraterrestrial surface is given, introduced, and also wheel slip is also introduced in the developed model. This is the newly developed model which can be used to predict the sinkage, which is based on the experimental results. Yeah. So this is the table that shows different A and B sinkage constant expressions. Using this, you are able to find out A and B, and therefore you are able to get A and B for this. And with respect to experimental value, you are able to predict the sinkage. That is how you are going to do. And this A is a function of number of lugs. N is nothing but number of lugs. If you add 8 number of lugs, you can add 8. If you want to add a number of lugs as 15, you can add n equal to 15. Like that, you are able to find different A and B constants, and therefore you are able to get different sinkages with respect to your wheel parameters, whatever you consider for the study. So finally, I will once again repeat. Yes, we were able to get some kind of inference from the results drawn from the wheel sinkage. One is increase in wheel slip results in decreasing the wheel sinkage in experimental results. Also, we were able to draw one more conclusion. With increase in lug height, you are able to reduce the wheel slip. Therefore, you are able to get the less sinkage. And we will also concluded rather increase in lug height, increase in number of lugs always results in giving a lower minimal sinkage. That is important conclusions that we were able to draw. And now I will try to show how it is affecting the mobility performance. Each and every parameter I will talk, and I will show how this mobility is getting affected because of that particular parameter. If you see these two plots, the plots are between the wheel slip and sinkage. And these plots are similar to the results which I have shown in the previous slide. Yeah. So from this slide, from this from the first plot, you are able to understand. Yes, you see here that blue color indicates that n equal to 16. Okay, that line indicates the number of flux used as 16. And green indicates the number of flux used as a 12, and red indicates the number of flux used as 8. So here, when you use n equal to 16, you are able to get the minimal sinkage compared to the number of flux when you use as 8 and 12. And that too, when you talk about the lug height, for h equal to 10 and h equal to 15 and h equal to 5, and you are able to see the minimal here at h equal to 5 at the minimum sinkage, that is 8 for this particular n equal to 16, number of lux as 16. Similarly, for this large wheel also, you are able to understand this red, green, and blue. That blue is when you are using n equal to 16, and when blue green is when you are using n equal to 12, and when you are using n equal to 8, this red line. So you are able to understand this blue is giving you lesser values compared to the above two different lines. And that too, when you compare this h equal to 10, 5, 15, you are able to get the minimum value for this h equal to 5 as something around 8. So 7.33, this is 7.77, something like that. So this is how you are going to define the mobility performance. The minimum sinkage means it is giving a better performance than the other combinations. So that is what you need to understand from this, plots. Yeah. Now, so I will go to the another parameter, slip ratio. So we were able to understand how this sinkage is affecting the probability performance, and also we'll try to see the slip ratio how it is affecting the mobility performance. You see this is the slip ratio arrived for a plane wheel. Okay, this is a plane wheel. Whereas these combinations, this portion is all related to the different combination of lux. When you add different number of lux, like n equal to 8, n equal to 12, n equal to 16, these slip ratios are arriving. And when you use plane wheel alone, your slip ratio is coming under like this 0.31 or something like that, 0.31. Okay, so we know that the slip ratio comes between 0 to 1, and 0 always indicates a better mobility, or 1 always indicates a worse mobility, and in between any values it depends. Okay, so here we were able to get for plane wheel 0.31, which is having a very good mobility condition. And for all other combinations, you are able to get lower, I mean, whatever combination you take, our slip ratio is ranging between 0 to 1 only. Everything is falling under 1. Okay, all things are giving a good mobility only. Okay, but compared to all combinations, what is the most effective one? That is what we have to draw. So here, when you see in that aspect, you are able to get a very minimal slip ratio, which is 0.45 compared to all other combinations. At h equal to 5 and equal to 12, we were able to get that value. So that is this. Okay, so this is the combination where you are able to get the minimum slip ratio compared to all other combinations. So this, I can absolutely say, gives a better mobility than other conditions. So that is what we can able to draw from this slide, this from this plot. So this is all about the small wheel slip ratio and the effect of wheel diameter on the slip ratio and the slip ratio on the mobility. So now we will see how this large wheel do that. Yes. See here, large wheel. This is a plot for the large wheel. Remember always the earlier one for fixed width. Okay, 32 mm. Okay, we are not changing the width. We are only changing the diameter. And here the for fixed width 50 we are changing the diameter. And also you can compare when you increase the wheel width from 32 to 50 what is its performance? That also you can able to draw conclusion. Okay, so let me show you here once again. Yes, you can see here for plane wheel you are getting most optimal, minimum slip ratio value, and whereas for other combinations, no, you are able to get a minimum slip ratio at this condition. So remember here also the slip ratio is falling under the range. It is between 0 to 1. We are getting the maximum as 0.7, which is far less than the 1. So all combinations are giving good mobility. But among all possible conditions, all combinations, what is the best one, best effective one? So the best effective one is this combination. So when you use n equal to 16, h equal to 15, you are able to get the minimum slip ratio as something around 0.53. Okay. Whereas when you see the plane wheel, you are getting the minimum slip ratio as 0.26. So these two combinations, you are getting the better mobility than the other combinations. Okay. So that is what you can draw from this plot. Let us go to the another parameter. So far, we were able to see how the sinkage is affecting the mobility performance, how slip ratio is affecting the mobility performance. Now we'll see The another parameter, the compaction resistance. We were able to study the motion resistance. No, the motion resistance is a combination of compaction, bulldozing, rolling, and gravitation. In this particular study, we have come across with the compaction resistance and rolling resistance. These two resistance, how it is, influencing the mobility performance, that we will see with this plot. We were able to draw plot between wheel diameter and compaction resistance, which is obtained with the empirical relationship by feeding the experimental results, experimental values. So you see again different color lines. So these color lines indicates different number of flux when you use n equal to 16, n equal to 12, n equal to 8, and you are able to get the minimum resistance at when you use n equal to 8, that is this one, okay, and h equal to 15 mm. So of course, all other combinations are also giving us a very less compaction resistance. Of course, these are also suitable one, but the most effective one we were able to find out, the most optimal one. Okay, when you use h equal to 515 mm, and you are going to get the minimum compaction resistance. For particularly when you use n equal to 8, so for this condition, it gives a better indicates a good mobility for that particular combination. Okay, that is how you are able to understand now. We'll see another one. This is for small wheel, okay, and similarly for a large wheel also you can able to see the same trend. So different lengths with difference in change in values, okay, but the minimum value, the optimal value rate for n equal to 8, h equal to 15. So this is how you are getting the minimum compaction resistance, where you are able to identify it is giving a good mobility compared to other combinations. So now we understood the compaction resistance, one of the parameters, how it is influencing, how it is showing the values, as well as how we are able to conclude, which is giving a effective mobility. Okay. Now let me show you another important parameter, how it is giving us the relation. Yes. Yeah. So far, this is the only only terrestrial surface. Okay, on the Earth surface. When you talk about the extraterrestrial surface, that also you are able to find using the empirical relation. The same trend is noticed. You see here, and here you see this is the line. Only difference comes between these values. When you take the experimental value, these values are changing. When you take the extraterrestrial surface, we are getting much lesser. Of course, you know the gravity effects comes into picture. Okay, Moon's gravity is 1/6 of Earth's gravity. So definitely you will have a huge difference in values. So you are able to even conclude that you are able to get a better mobility for a condition when you use number of flux n equal to 8, okay, and h equal to 15. This is for small wheel and this is for large wheel. So the same thing, only the difference comes between here, change in values. But the trend is same. For n equal to 8, h equal to 15, we were able to draw a minimum compaction resistance where it indicates a better mobility than other conditions. Remember, these conditions also gives a better mobility, but most effective one is this combination. Okay, so that is what we need to understand from this. Now let us move to the next resistance. Okay, so this is the combination. This is another important rolling resistance comes with the motion resistance category, and we will see how this is giving a mobility performance, how it is affecting the mobility performance. Now you can notice this picture in the rolling resistance. So with increase in lug height, you are able to get the maximum rolling resistance. Rolling resistance is increasing with respect to the increase in lug height. Each and every case is like that only. Okay, you see here, when you use n equal to 12, when you use h equal to 5 to 15 mm, there is increase in rolling resistance. Similarly, when you notice n equal to 16, there is increase in rolling resistance. But when you compare n equal to 8 to n equal to 12, n equal to 12 to n equal to 16, with increase in number of flux, what is the result? Okay, with increase in number of flux, you are able to reduce the rolling resistance to a certain you know to certain extent. Okay, so this rolling resistance compared to other two combinations, this is getting very low value, and that too for h equal to 5 mm. That is what I have mentioned here. Comparing all values, you are able to get the minimum value. This RR, which is nothing but rolling resistance. the minimum value for n equal to 16 when h equal to 5. This is the most important conclusion that we are drawing. And similarly, for a small wheel also, you are able to compare n equal to 8 to 12, 12 to 16. You are able to get the minimum rolling resistance for this n equal to 16 when h equal to 5. So that is what I have mentioned here. So 12 and 11. When you talk about only plain wheel, so always the plain wheel is giving a lower rolling resistance. That obviously good, but our motto is we need to improve our mobility performance. We need to investigate which combination is giving a better mobility. So for that we were able to do this research. We are introducing n equal to 8 to 16 as n equal to 8, n equal to 12, n equal to 16, and also you are introducing h equal to 5 to 15, h equal to 5, 10, and 15. So you are seeing all possible cases. Out of all possible cases, you are going to get the best optimal combination for its better mobility. Okay. Yes. So this is about the rolling resistance. You are able to get less rolling resistance for that particular combination, which indicates the better mobility. And now I'll show you next slide. Yes, the rolling resistance is a function of coefficient of rolling resistance. This coefficient of rolling resistance is a function of sinkage and diameter that we have seen in the previous slides. So now I plotted between the wheel diameter and the coefficient of rolling resistance, and from the various sources, I am able to classify the mobility class as like this. Okay, so different CRR values are given here. You see when it is less than 0.2, it indicates good mobility. When it is ranging between 0.2 to 0.3, it is indicating fair mobility. When it is zero point 0.3 and exceeding 0.3, it indicates the poorer mobility. So this is the mobility class is defined based on the CRR value. Okay, so here you see the picture, the plot which is plotted between wheel diameter and CRR for the small wheel as well as for the large wheel. So you are able to, this is plane as well as this is the different combinations. So you can able to see the CRR how it is varying with respect to number of lugs, with respect to different lug heights. Okay, so you are able to get a minimum CRR like for small wheel point something around 0.21. So which comes between 0.2 to 0.3, and this is given as fair class, fair mobility. The mobility is given under this fair class. Okay, for this combination. Whereas it is nowhere it is exceeding 0.3. Okay, so everywhere it is fair, but we can consider the most minimum value. Okay, based on the available cases. Here you see, you observe maximum touching is 0.3. So maybe this is the case where you are going to get the poor mobility. But wherever other things are comes between this 0.2 to 0.3, which is giving you a fair class, fair mobility. When you come to the large wheel, okay, see it is just way far less than the 0.3. It is at least a small wheel is reaching a 0.3, whereas this large wheel is nowhere nearing this 0.3. Your everything is below 0.3, which is almost a maximum as 0.26 or something like that. But you are going to get the minimum for plain wheel. Obviously, when you compare other combinations, you are going to get a very minimum CRR for this particular combination. When you use when equal to 16, when you use h equal to 5, so you are able to get 0.18, which indicates which is less than 0.2. So for this combination for large wheel, the mobility class is classified as good. Okay, not only fair, it is good, very good, good mobility. It is indicating good mobility. So this is how you are going to derive the mobility performance of a particular rover or a rover wheel based on the compaction resistance, rolling resistance, CRR. Okay, let me show you another one. Yes, finally we were able to plot between the rolling resistance and compaction resistance. Coefficient of rolling resistance. So same thing, whatever you see in the previous slides, you are able to see here. This is the plane wheel, okay. Whereas the all other things are combination of various cases, various number of lugs with different lug heights. So here x is nothing but CRR value, and y is nothing but RR rolling resistance. Okay. So for this condition, we were able to get the minimum rolling resistance as well as the minimum CRR value, where this combination indicates a good mobility and fair mobility compared to others. Okay, so that is the conclusion you can, that is the inference that you can draw, and that is the conclusion you can make. Okay. Okay. With this, I will also try to show you another important parameters. So, okay, see, so far we were able to see how that slippage is affecting the mobility performance, and how that slip ratio is affecting the mobility performance, and also we have seen compaction resistance, how it is impacting the mobility performance, and later we were able to see rolling resistance and coefficient of rolling resistance, how it is affecting the mobility performance. And now we will move into other important parameter, drawbar pull. This is the last parameter we are discussing, and that is the drawbar pull, how it is influencing the mobility performance on a terrestrial surface as well as on the extraterrestrial surface. You see the pictures, the plots here we drawn between slip ratio and drawbar pull. Okay, so now, so we know that we need to have a more pulling ability, so in order to get a good traction. Okay, so good traversing condition. Okay, so here you are able to identify and able the condition here. Okay, and obviously, these are the various, 1 minute. So these are the various combinations of slip ratios with respect to drawbar pull, okay, that are given. So we were able to get the maximum drawbar pull for this combination when n equal to h, when n equal to 16, h equal to 15. This is where you are getting the maximum pulling ability. So this is where that indicates the better mobility than the other combinations. Okay, that is what I mentioned here. Okay, for a small luggage wheels, the maximum drawbar pull attained is 45 newtons, whereas when you see the large wheel, okay, similarly you are able to get the maximum drawbar pull as something like this. But n equal to 16 and 80, so it comes under you. So you are able to, you have to take the maximum, giving performance. So we are able to understand, introducing the various combinations. We were able to see how this mobility performance is, getting. So out of which we are able to draw the best combination for getting the effective mobility performance. Okay, so that is what I want to show, this drawbar pull effect on the mobility performance in case of terrestrial surface. Now I will show you this is affecting the extraterrestrial surface, and this is conclusion for the extraterrestrial surface. Yeah. Now you see. Sorry. Now you see here. Yeah. Same for extraterrestrial surface also, we were able to get the maximum drawbar pull. Okay, but we are getting the change in values here compared to the terrestrial surface. Okay, the maximum drawbar pull we are able to get for this combination, n equal to 16 and h equal to 15. Okay, and here also for large wheel, we are able to get the maximum drawbar pull for n equal to 16, h equal to 15. Okay, for this value out of all the combinations. So from this, we were able to understand we are getting the mobility performance, good mobility performance for all combinations, but comparing all combinations, you are able to satisfy this more effectively for this combination in the extraterrestrial surface too. So this is how this various parameters that influences the mobility performance of a particular rover B. So coming to the conclusion, complete summary of the presentation. Yes, we were able to see, understand various, parameters which talks about the mobility performance, which comes under trafficability studies, and we were able to understand what is thermal mechanics. We were able to discuss a brief, get the minimum linkage for all the combination, and we need to know that the increase in number of lugs along with the increase in lug height always gives us the minimum linkage. Also, we were able to draw a conclusion, even if you go beyond number of lugs as 16, like you use 20 or 24, something like that, or even you go on increasing the lug height, maybe that will give you a better results. So there is a, one of the inference that is drawn from the experimental study, and also we were able to understand how this syncage is giving affecting the mobility performance, and also we were able to understand from the experimental results the predicted values are much lesser than the experimental results, and therefore a mathematical model is introduced and developed, which is with an introduction of syncage constants AB, which is a function of number of lux n, okay, with the introduction of gravity effect and wheel slip. So that is what we have seen. And also when you talk about different parameters, we were able to understand the minimum slip ratio arrived as 0.45 for a log height when you use n equal to 12 and h equal to 5 mm for small wheel, and for large wheel n equal to 16 and h equal to 15 as 0.53. And similarly we were able to understand for different resistance, like compaction resistance, we were able to get a lesser compaction resistance for this combination h equal to 15 and equal to 8. And similarly for large wheel, and also rolling resistance, we were able to get the minimum for a certain combination when n equal to 16 and h equal to 5. After this we were able to tell lower the resistance to better the mobility. And also we were able to see how the CRR ranges between different values, how that mobility class is defined based on CRR values. We know that when CRR is less than 0.2, it is given as a good mobility. When it is ranging between 0.2 to 0.3, it is given as a good fair mobility. When it is less than 0.3 or 0.3, it is given as a poor mobility. So for the considered combinations, we were able to get all CRR values less than 0.3, ranging between 0.2 to 0.3, which indicates a good mobility, and also fair mobility, which indicates which we are able to draw a most suitable combination with the lowest CRR value compared to other combinations. Similarly, when we have seen drawbar pull parameter, we know that maximum pulling ability you need to get it for a rower wheel to have a good travel on a planetary surface. Yes, we were able to get the maximum pull for the combination h equal to 15 and equal to 16 for both large and small wheel. And with this, we were able to conclude the study. The most feasible and optimal dimension for a wheel, when you introduce a number of flux as 16 and h equal to 15 mm, that combination will give you the most suitable combination, like most suitable optimal dimension to travel on particular TRI1 lunar soil simulant, and which is done in the trafficability studies. We have examined all the, with examining all the limits. So that is all about the conclusion. I will show quickly about the research contribution. What are the research contribution through this research study? Yes, you are able to find out the limitation in order to investigate and develop a model. And one of the we were, and another important do applicability to studies combination on that particular TRI1, on that particular TRI1 lunar soil simulant. And most importantly, we were able to use 16 when you are using that particular rower wheel on that particular terrain, this TRI1 lunar soil simulant. That gives you the better mobility within the cases that are examined. So this is the research contribution from the particular research study. And also coming to the reference and publication. So these are the publications based on the research contribution and research study. We were able to publish on material science and engineering, and we were able to publish on the Journal of Thermomechanics, which is a very good journal, and also we were able to publish in this. So these are the various publications. Now I'll quickly show you in few minutes about what is the research scope. Okay, what is the research scope in this area? Yeah, so we have seen particularly few parameters. Still we can able to do more work on various trafficability parameters, which is indirectly or directly showing the improving the mobility performance. We can try to work on various. See, we have a lot of landing sites. So for example, I have taken Apollo 16 as a landing site example. So for that we were able to, for that now it is we are able to make that TRI1, and on that we were able to conduct research studies. But whereas so many machines are there where you got a lot of problems, but that machines you are able to conduct these studies. Yes, and mobility on rough terrain. So these also you can this is something on sensing ability. So when the obstacle is there, some things like sometimes the rover gets stuck there, and it is therefore it is not able to move anywhere. So that sensing ability must be focused and do by kind of research on that. You can improve the sensing ability in order to avoid such kind of problems. And similarly, suspension, okay, climbing ability, okay. So when you have an obstacle, sometimes it is not climbing. You need to introduce that climbing ability to that particular rover, and you need to focus on this. This is the future scope. You can work on it. This is how you can climb and move. Okay. Another important future scope is this sinkage effect. You can still investigate more on this particular sinkage effect and how we can improve that. And also you can work on suspension type. We have a particularly rocker box suspension, something like that. We have a lot of suspension types are there. You can still modify, introduce some innovative things, and try to give better solution for the problem. Different suspension movements you can able to see here, and similarly suspension with mobile climbing ability. So this is where you can focus as a research scope. With this I will try to conclude. Yes, my session is done. If at all, if you have any doubts, you can raise me now. I think my voice is clear, right? Throughout the session, there is no breakage.
Yes, sir. Thank you very much, sir, for your excellent presentation.
Thank you.
Now, I request the participants, if you have any questions, you can directly unmute yourself, or you can type them in the chat box. We'll disable the chat box. You can type there, or you can directly unmute and ask him.
Okay, I'm Dr. Nagu.
Sir.
Hello.
Sir. Yes, sir. Yes, sir. Please, sir.
Yeah, excellent presentation. I think it's first of its kind so far.
Yes, sir.
Rover
Actually, India people are not doing this research. Only in Japan, Russia, and USA they are doing They have very good facility, laboratory facilities. Even
yeah, in spite of that, you have made a good beginning, and also did to the extent possible with the available things. It's very inspiring. I congratulate you for an excellent work, Dr. Parla Girish Kumar. Thank you.
Thank you so much, sir. Thank you.
Good afternoon, Dr. PJ Kegar. Good afternoon.
Sir, good afternoon, sir.
From Kids Guntur.
Yes, sir.
You have given very excellent session and very informative. It is very lucid manner and it is very understandable. Thank you. Anyhow, once again, we are expecting same thing from you, sir. Thank you.
Yes, sir. Thank you, sir. Thank you, sir. Thank you so much. Yeah, there is one question. I'll read that question. Lunar soil strength parameters simulated in lab existing systems. Okay, it is not a question. You're just saying. Now, what we have done is the TRI one. Okay, like I will. The TRI1 lunar soil simulant, we have collected different set of grades from ISRO Bangalore. So we have characterized that different grades to a particular simulant that we named it as a TRI1. Okay. So India's first lunar soil simulant. That properties resembling that Apollo 16 landing site properties. Okay. Whatever you call it as a cohesion, friction modulus, and you call it as a density, you call it as a sinkage exponent. So all these different parameters are there, soil properties. That soil properties are resembling that Apollo 16 landing site properties. So that is how we have done. We conducted plate load test to define sinkage constant, sinkage exponent, and we did direct shear test. We did different XRD and SEM in order to characterize that TRI1 lunar soil simulant. Like that, we have done the experimental part and we have incorporated that. And also the software is also there for this particularly. Maybe you might be hearing that Adams software. Okay, that Adams software and CATIA will be used to kind of do that dynamic analysis. Okay, even you can use FEM ANSYS also, because in the previous phase two, I have given a presentation of FEM applications in terra mechanics, where I studied the different stresses that they are developing when that wheel interacting on the surface of the soil, and also I have studied the deformation and displacement analysis in that study. So like that you can do, you can model in that SolidWorks software, you can import that into the TEM, even Abacus and ANSYS. And if you want to do in particularly in most dynamic analysis, you can go with the Adams or CATIA. So then you can see that different, whatever I showed, climbing ability, you can even have that kind of analysis. Thank you, sir.
Sir,
There is a
good
lot
morning,
of scope
sir.
on this.
Good morning, sir.
Nazir sir. Nazir sir, good morning.
Sir, very excellent presentation, sir. So far, we have conducted so many research areas in our related to our planet, but you are conducting the research related to extraterrestrial, and that too a rover which when the crisis is developed. So already we have seen so many in the Mars also recently. So how you have got the data, sir? First of all,
Yes, sir.
because the gravity is different now compared to our Earth
Yes,
planet.
gravity. Yes, sir. Yes, sir.
So then, how you have calculated
Yes,
the
sir.
weights? Is there any simulation software you use it, sir?
Yeah. I will address this question. Thank you, sir. Because many of us might be having that gravity effect will be there. No, moon's gravity is 1/6 of Earth's gravity. Obviously, the things will different coming to the
Yes, sir.
terrestrial
We have
surface.
already
What we have
learned
done is we
Newton's
have data from
Newton's
ISRO,
law
like
of
ISRO
gravitational
we took.
forces, sir. But
Yeah.
have you
Yes,
used any software, sir?
sir.
That is
Yes, sir.
my question.
Yeah. We used that different softwares like that Adams I'm mentioning you, Adams software. So you can give that all inputs related to the gravity or related to the whatever the extraterrestrial properties that you are having, conditions you are having, that you can create. At present, I don't have that picture to show you, but I have in my system. Okay, in this laptop, I don't have that data. If I have that data, I might have showed you. We have generated that on the particular software. We have Adams software. We have a Mars exploration rover simulation software also. Okay, or ROPT, some other software is also there. So with that software, you are able to input all the data and you are able to simulate that how it is coming. That simulation parts you can able to draw that results.
So one question, sir. Then
Sure.
Then how you have calculated the soil properties there in the extraterrestrial object there?
Yeah. This I will tell you. I mentioned in the just before some time. We took different grade soil samples from the ISRO Bangalore. They got that samples. Okay, like
Okay.
12 grade of samples. So these 12 grade of samples, what we have done is we were able to characterize all these samples using XRD, SCM, spectral microscopy, and XRD also, X-ray diffraction. So using these tests, we were able to characterize those sample. This TRI1 lunar soil simulant, which I am telling the term. TRI1 lunar soil simulant. So this
Okay.
properties we were able to conduct, whatever we call it as a direct shear test, you call it as a compaction test, you call it as a, what is that? Plate load test. For this soil sample, because this soil sample properties we were able to get, that properties is resembling those properties. I have showed some rovers, no sir, types of rovers, Apollo
Yes, sir. Yes, sir.
lunar roving vehicles. So in that we have Apollo 16, Apollo 14, Apollo 17. So what they have done, that Apollo missions have sent the data to the NASA and ISRO. Okay, so they have that particular data like properties of soil. So you take density. What is the density? Because that Apollo 16 explored the space. Okay, and it was able to give the properties. So that properties we matched with our experimental data. So since it is matching, we call it as a TRI1 lunar soil simulant, which is resembling that properties. Okay, when you are sending that machine to that particular landing site, you can use this results and you can use that optimized design what we are giving. So then you can get the better performance. Like that we have done.
Anyhow, very innovative, sir. Very excellent this thing in this kind of research. I congratulate you, sir, for your presentation. Thank you, sir.
Thank you, sir. Thank you, sir. Thank you very much. There is another.
Dr. Girish Kumar, 1 minute.
How do we?
Hello.
Sir, Nagu, sir.
Yeah, just
sir,
now
please tell
regarding
me, sir.
the value of everything you can, because from the soil properties you are able to articulate the soil. And
Yes, articulate the
what
soil.
about the physical gravity difference issue between the Earth and the planet? For that, there will be some
Sir,
equivalent weights, something like that. Because G value.
sir, we have some empirical relations. Yeah.
Yeah. Okay. Yeah.
So
Please.
we have some empirical relations given by previous people, previous scientists. They have worked on NASA and with NASA and Russian space machines and all. So with the help of them, like their empirical relations, they were able to incorporate that gravity effect on that particular relationships. So whatever the experimental values you are conducting on the terrestrial surface, you can feed it indirectly. It will have that gravity effect. Okay. See, whatever results I have shown, like drawbar pull on the terrestrial and extraterrestrial surface, we are getting kind of 50 or 20, 25. But whereas in extraterrestrial surface, you are able to get 2, 5, 6, something like that. There is a huge difference. But
Okay. Thank
still,
you. I only felt there will be an equivalent weight relationship. It's not that simple.
no,
Then.
no.
Okay. Fine. Thank you.
Thank you, sir. No, this is not. That is articulating soil is not so simple. We have done a lot of combinations. We have done a lot of XRD analysis and we have done SEM analysis. After doing a lot of investigation, only we were able to articulate that soil simulant. It's not that so easy. With the help of another scholar as well. So thanks to all the participants for this participation. Madam, you can conclude, madam.
Sir?
Yeah, you can proceed, conclude.
Okay, sir.
Maybe.
Participants, we are concluding the session now. Okay. We'll share the PPT if possible. Sir?
Feedback link will be provided, ma'am. You have
Yes,
already
sir.
provided. Please
We have
tell them.
already
Yeah.
provided the feedback link. You can give the feedback. Also, we'll share the PPT while after the completion of all these sessions, we'll share the material and PPT of this one. And also, we are very thankful to you for participation. And we'll meet in the evening session, which would be addressed by Mari Samanathan. We'll start the evening session and we'll meet there. Thank you everyone for participating. We're closing the session now.
Yeah, yeah. And one more thing I want to tell you, we have a Mars 2020 rover mission. Okay, there are so much of research is happening in Russia, Japan, and in India also in IIT Kharagpur or IIT Kanpur and IIT Madras very recently. People are doing there, one or the other one. So, but most important, this research used to happen in China, Japan, USA, and Russia. So there is a Mars 2020 that we are doing it. Okay, and also people are investigating, the sustainability on lunar planet also. So there is a huge possibility for civil engineers also to do multidisciplinary research. Maybe if anyone search in that aspect, I request them to see the foreign universities. They are doing extraordinary work in these areas. For me, that was my main interest. That because of that, I wanted to do some research on space. So I did this somehow in some way. But if you have more facilities, I could have done even design of a complete rover. But since there is lack of facility, I was not able to concentrate. Maybe in future, maybe in a couple of years or something, I'll try to even design kind of a small rover at least. I would like to work on it. So we request all the participants to come back again at 4 o'clock for the continuation of the hands-on experience on N-Logic. And tomorrow we will have a tutorial on Fuzzy logic, Fuzzy system in Fuzzy logic in civil engineering applications by Dr. Rovers sir from IIT Madras. And then later we will have the validation part in tomorrow's morning session. So kindly join today evening at 4 o'clock and tomorrow morning at 10 o'clock. And also we have a small assessment also. So maybe if you attend tomorrow's tutorial class, you can understand how the Fuzzy is applicable to our civil engineering applications. That was really interesting. Fuzzy is a lot of research scope is there in Fuzzy and all software computing techniques. You know, you can even your papers also can get accepted. All, even myself, I am doing in transportation. I was wondering that transportation application can also be used for this. Fuji also can be used for this transportation. That's why I'm also very much interested to know that. So I request all the participants to also equally come and participate. If you want your students to also join, you can ask them to join and understand the basics. Thank you once again for all the participants. I hope you are getting the feedback. We'll meet once again in the evening session. Thank you.